Hi everyone. In this video we're going to look at the method of least squares that we use to determine which linear model fits a set of data better. And ultimately how we determine the best linear model. And you might see this abbreviation LSRM along the way, and that is going to stand for least squares regression model. And so it's a very intuitive process that we'll look at here with a couple of different examples, and we'll come back to that term. So this is a set of data. It's plotted over at the right with a student's line of best fit. They say is the best fit off of this data. Negative x plus 11.8, and it's drawn on there. And you might be skeptical of this. You might say, well, I think there's a better line. So you'd get your pencil and paper out and play around, or you'd plot the data points. You'd say, somewhere negative sloping sounds good, but maybe I don't know, maybe not quite that. Maybe you think this one is a better line right here. Looks pretty good, right? So negative 0.8 plus 10.95. You may not agree with me, but we're going to look at the numerical way of determining which set of data is best. And it's going to feel a little bit like standard deviation when we calculated it, but we're going to stop a few steps short. So the data table is right here, and what we need to do is figure out basically which line has the least amount of error in it. So we're going to calculate out some residuals, and a residual or an error, those terms are going to be interchangeable here. Residual is always, I just remember this is alphabetical order, it's observed minus the predicted. On the graph, you can see these errors as vertically how far away from the line each of these data points is. So we need to know what our predicted values for y are, and we're talking right off of our line equation. So this is for the student's prediction. Put in 10 for x and you get 9.8. Put in 7 for x, or sorry, put in 2 for x and you get 9.8. Put in 4 for x and you get 7.8. And you notice the slope's -1, so if we go over 2, we're going to just go down 2, so this will be 5.8 when we plug in 6, 3.8 when we plug in 8, and then 1.8 when we plug in 10. And these are points that are actually on the line of fit that we're talking about here. Then we're going to find the errors, so we're going to do observed minus predicted, the residuals also, so negative 0.8. 6 minus 5.8 is 0.2. And then 5 minus that is 1.2. And if you add up this total, just like we did with standard deviation with the residuals or the errors, we're going to get 0 every time. So come on over here and square them. We're just going to square them to get rid of our negative signs. 0.64, 0.04, 1.44, and then 0.64 again. And then we're going to total these. And this should be 2.8. Now, is this the smallest error? Well, remember we call this the method of least squares. We're looking for a least square regression model. So is this one the smallest? LSRM is an abbreviation you'll see. So is this the smallest error? Well, we can go compare it against the one we did. Oops, not that one. That was the last video. The one we did over here, and we said this was the better line. And here's a visual way to see the squares. This area would be whatever this residual is, squared all the way down here. And if we look at the sum of the squares, you notice it says 2.87. Well, our estimate has a bigger sum of the errors squared, so our estimate has more error. This estimate is a better model. And you can verify this on your calculator and see that this actually is the line of best fit that the student